Hello again, everybody. In this video, we're going to start chapter 14, and chapter 14 is about binomial distributions. Binomial distributions, big part of the methods course, and there's a fair bit to understand. It probably builds off our knowledge of tree diagrams, but there's a few extra conditions that we need to be aware of when it comes to binomial distributions. First thing that we actually talk about is the idea of a Bernoulli sequence. And a Bernoulli sequence or a Bernoulli trial refers to a single event with only two possible outcomes, right? That's a really key feature of Bernoulli sequences and binomial distributions, that there really can only be two possible outcomes. So it's often like a yes or no situation, like where something can either happen or not happen. Often this is referred to as success or failure, but the key idea being we've really only got two possible outcomes. And the other key, so I guess only two possible outcomes, really important to understand, but also each outcome has a fixed probability, and that doesn't change sort of throughout the situation, okay? They're the two key features. So for example, when you roll a six-sided die, if you're only interested in whether you get a 4 or not, that is a Bernoulli trial because you've got, one event which represents success, right? You can roll a 4, which would give you a probability of success of 1/6, or you can not roll a 4, which of course is all the other possibilities, so that's 5 out of 6. So for this first example, the question says, state whether the following cases are Bernoulli trials, and if so, state the probability of success and the probability of failure. So for the first one, selecting a king from a standard deck of cards. So if we had a shuffled deck of cards and we're going to pick one card out, the probability of, if we were interested in whether we select a king or not, then that is a situation where we only have two possible outcomes and there is a fixed probability. All right, so this would be yes, that's a Bernoulli trial. The probability of success, which we often use lowercase p to represent, well, there are 4 kings out of 52 cards. So the probability of success would be 1 out of 13. And that means the probability of failure, the probability of not getting a king, would be 1 minus 1/13, which is 12/13. All right, so that is a Bernoulli trial because we've only got two possible outcomes. We either get a king or we don't get a king, and the probability of success is 1/13. Okay, another situation, determining what mode of transport a student uses to get to school, where the options are car, train, bike, or walk. Well, straight away, there's 1, 2, 3, 4 possible outcomes. So this is not a Bernoulli trial, right? Because remember that a Bernoulli trial only has two possible outcomes. So that one's just a no, it's not a Bernoulli trial. Okay, the binomial distribution is a situation where you have repeated Bernoulli trials, right? So the same conditions we just talked about, two possible outcomes, each outcome has a fixed probability, but we do the trial multiple times, right? 2 or 3 or 4 or 5 times over and over again. So common examples are tossing a coin multiple times, drawing balls out of a bag with replacement, right? So when you actually put it back and then do draw the ball out again. Shooting basketball free throws, you might take 20 shots at the basketball ring in a row. So it's a repeated trial. And so, as we said, as a bit of a summary, a binomial experiment is one that has the following properties. A series of identical trials. Each trial has only two outcomes, right? We'll keep kind of emphasizing that, only two outcomes. And the probability of success is the same for all trials, right? So the probability of success stays the same. It's not a situation where the probability changes from one trial to the next. Often we use a variable, most commonly x, but it doesn't have to be, capital X to represent the number of successes. And we call this variable a binomial random variable, and it's said to have a binomial probability distribution. Okay, and we'll kind of get more into this as we go through some examples. This is another little bit of notation that you might see. This sort of this notation here. This is just a way of representing a variable x and indicating that it's a binomial variable with n number of trials. So n is the number of trials, and the probability of success with each trial is p. Right, so that notation is often used as a bit of a shorthand to say this is how many times we're doing the trial, and this is the probability of success with each trial, with each time we do this experiment. Okay. Example 2 says, a coin is thrown 3 times. Let x represent the number of heads. Find the probability that x is equal to 2. Right. Now, this is a common kind of tree diagram question that we've done before. I'm actually going to do this one without drawing the tree diagram, although I'm sure you can imagine what it would look like with heads, tails, then heads, tails again, then heads, tails again. But we know that if we wanted, so if x represents the number of heads and we want x to equal 2, this question is just saying, find the probability that we get 2 heads exactly out of 3 coin tosses. And that can happen 3 ways. You can get heads, then tails. You can get heads, then tails, then heads. Or you can get tails, then heads, then heads. Okay? And each of these have a probability of 1 out of 8 of occurring, right? So the probability of heads, heads, tails would be a half times a half times a half. Same with heads, tails, heads. Same with tails, heads, heads. So it's really 1/8 plus 1/8 plus 1/8, which gives us 3/8. So really in a situation like this, what we have to work out is how many different ways can this number of successes occur. And then you can kind of multiply the probability of it occurring by that many. So each of these sort of events had a probability of 1/8, and there were 3 different ways it could happen, so we got 3 times 1/8. Okay. Here's a slightly more complicated question that, again, we can kind of think of using tree diagram methods. This says, in a particular country, the probability of a female child being born is 0.52. So when a child's born, the probability that it will be a female child is 0.52. Find the probability, correct to 3 decimal places, that a family with 4 children will consist of. Okay, so a couple of things to pick out here. One is that the probability of success is 0.52. And 2 is that it's a family of 4 children, so the number of trials is 4. Okay, and we know this is a binomial situation because there's no indication that somehow this probability is going to change. So depending on what the first child is, that's changing the likelihood of the second child. It's just a fixed probability for each of these 4 events, or 4 trials, I should say. So if we wanted to work out the probability of getting 4 daughters in a row, again, you could draw out a tree diagram with female, not female, female, not female, and set it all up. But if you understand how a tree diagram works, you can just go straight away to, well, let's say the probability, actually what I should do, let's introduce the variable first. I'm going to say let x equal the number of female children, because that wasn't explicitly said in the question. So the probability that x would equal 4 is really the probability that we get daughter, 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 4 times in a row, which is 0.52 times 0.52 times 0.52, it's just 0.52 to the power of 4. Right, we want it to happen 4 times in a row. And on our calculator, we can crunch that pretty quick. Question said 3 decimal places, so in decimal mode, we get 0.073. 0.073. Okay. The probability of getting exactly 3 daughters is a little trickier. The probability that x equals 3, the reason this is trickier is because there's actually a few different ways that this can happen, right? In part A, we just wanted 4 daughters. Now there's only one way that can happen, and that's if every child, first, second, third, and fourth, they all need to be female. But in the second question, if we want 3 daughters out of 4 children, there's actually a few different combinations that could give us that result. For example, we could get the first 3 children were daughters, they were female, and then the fourth was not. The other way that it could happen, or another way that it could happen, is that we could get the first two children being female, then the third one's not, then the fourth one is, right? So that gives us 3 out of 4. We could also get a female child, then not female, then female, then female. Or we could get the first child is not female, and then the next 3 are. All right, so there's actually 4 different ways that we can get exactly 3 daughters in this family of 4. Now, our next job is to find the probability, right, of each of these occurring and add them all together. So, using the p equals 0.52, we've got the first one would be 0.52 times 0.52 times 0.52, right? So we'd have 0.52 to the power of 3 times, now the probability that we don't get a female child, which is this fourth outcome here, is 1 minus 0.52, and in fact you can write that as q equals 1 minus 0.52, and that would be 0.48. Right, that's like if P is the probability of success, then Q is the probability of failure, right? So we're considering it failure if a child is born not female. I'll let you decide whether you agree or disagree with that. So it's 0.52 to the power of 3 times 0.48. That's the probability of getting female, 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 not female in that order. Okay, now let's look at the second calculation. We would want a female child born first, so 0.52, that's the probability of that occurring, times 0.52 again, times 0.48, times 0.52. Now that's actually just the exact same multiplication, but in a different order. But we know that multiplication, the order doesn't really matter. We're still, for this probability, going to be multiplying 0.52 3 times, and then multiplying 0.48. With the third calculation, again, it's going to be the same combination of numbers, just multiplied in a different order. It would be 0.52 times 0.48 times 0.52 times 0.52. So again, it's going to be 0.52 cubed times 0.48. And lucky last, it's going to be 0.48 times 0.52 times 0.52 times 0.52. So again, we're getting the same multiplication in a different order, but that's not going to change our values. And so you can actually see from this working out that a much quicker way of doing this calculation would just be to calculate this probability once and then multiply it by 4, because there's 4 different ways we can get this outcome. All right, so that actually is leading us towards the quicker way of working out binomial probabilities. Now, let's finish the question off because we've still got work to do here. It was 0.52 to the power of 3 times 0.48, right? And that equals 0.067 and the rest, right? Now that's one of them, but rather than add the same number 4 times, I'm just going to multiply that answer by 4. So answer times 4, and that gives me 0.2699. Now to 3 decimal places, that's actually going to round to 0.270. Right, so what we've discovered here is that the probability of having exactly 3 daughters out of 4 is 0.270. The last part of the question says, what's the probability of 3 or more daughters? So really this means, what's the probability that x is greater than or equal to 3? Well, again, we can think of this as the ways that that can happen. And the way that that can happen is the probability of getting 3 or more daughters means you either want to get exactly 3 or you want to get exactly 4. Right? And it can't be more than that because the number of trials is only 4. And in part A and part B, we've actually worked out those 2 probabilities. So it's 0.073 plus 0.270. All right. and can actually, already got those numbers on my calculator, so I can add the two together and get 0.343. Okay, now in the next video we're going to get into what we call the binomial, or sometimes referred to as the binomial formula, which does let you start taking some shortcuts. But this idea I think is really important to understand, that when we're doing these binomial calculations, it's about working out how many different ways can you get that number of successes, and then finding the probability of one of those ways and multiplying it by the number of combinations. So keep that in mind when you get to the next video.